Okay, we're going to be covering non-ideal gases today. And we'll start off a little bit with ideal gases and other properties. But what we're doing now, believe it or not, is we're done with material balances. Right? We've covered all the theoretical content that we can really with material balances, other than adding in complexity in how big the process is, how many different other things we work on, and all that. So today we're going to be starting to talk about properties of single-phase systems, meaning that I don't necessarily have to give you the mass flow rate or the molar flow rate. I can give you a volumetric flow rate. You can convert that using density and molecular weight. And so now we're going to talk about predicting and measuring properties of single-phase systems. So what do you think that the next step will be after single-phase systems? Multi-phase. What's the next step after that? Multi-phase, multi-component would be the next step after that. And then we'll move on to energy balances, and then that'll basically wrap up the class. So the goal of what we're trying to accomplish here is that I don't want to have to make the problem seem sort of trivial and sort of arbitrary. Right? I want to make the problem seem less arbitrary. Instead of saying it's 10% coming out of the top, right? I want to use thermodynamics to predict what is the amount coming out of the top, for example. Right? And then I don't say, oh, it leaves at 30 degrees Celsius. I want you to calculate what temperature it leaves at. Right? So we're adding in some complexity, but the material balance component is going to be the same. So now what we're going to be talking about for the next several weeks is what are the properties of streams, how do certain separators operate, how do we know what the outlet composition is based on the separator properties and operating conditions. And then lastly, we'll say, okay, how much energy does it take to run this process? What is the actual temperature coming out? And all that jazz. So the complexity is going to be introduced not in terms of the material balances, but in terms of the information that you're provided and the calculations you have to perform to calculate the properties of the inlet and outlet streams. Sound good? All right. So we're going to start off, before we get to the ideal gases and non-ideal gases, we're going to talk about liquid properties. So in general, liquid properties are very hard to predict. We do not have a good equation of state that can predict liquid properties. So if we look at our sheet here for gases, right, we have the virial equation of state, the van der Waals equation of state, the SRK, and the Peng-Robinson. Right? These are all, I would say they look like fairly complex equations. Right? These are really good at predicting most gas properties. They are really, really bad at predicting liquid properties, except for a few simple liquid mixtures, like simple hydrocarbons, like pentane or octane. Right? These can predict the liquid properties of those things. Now, one thing that you'll talk about in your Thermo 2 class next semester in the fall is that the ideal gas law is a really bad equation of state because it does not predict that liquids can even exist. Right? The simplest equation of state that can predict that liquids exist is the second one on your list, the van der Waals equation of state. And it's really bad at it too. Right? So we're not going to go over how equations of state predict that liquids exist, but just know that the ideal gas law, there's no way you can ever form a liquid with the ideal gas law. So you need to have a more complex equation of state. So with liquids, and in general for most properties that we're going to be concerned about, there are three different sources of information. So one, we can look up published data. Right? So if you want to know the heat capacity or the liquid or some other property information associated with your material, easiest way is to see if someone's already measured it. Right? What's the density of a 20% hydrochloric acid solution at 120 degrees Celsius? I'm sure that information exists out there somewhere in the literature. That's probably the easiest way to do it. So a piece of information that you may have seen or you will see is Perry's Handbook. Has anyone heard of Perry's Chemical Engineering Handbook? We have a few hands. You'll probably be very familiar with it, especially going through next year into senior lab. And the CRC Handbook. So CRC Handbook, I think of Chemistry and Physics is its full name. There's like 100 editions of this. They put one out every couple of years, updated with material property information. So between these two sources, you can usually find a lot. And if not, you can go to the peer-reviewed literature if it's a bit more of an esoteric compound. Number two, we can estimate the property. This is what we're going to be talking about for the most of it. And lastly, you can measure it. And this is what we would do, this is what would happen at an industrial lab. So if you're about to commit to building a multi-hundred-million or billion-dollar chemical plant, it's worth your time to measure the actual properties of the fluids that you're going to be working with. But for us, we're going to talk about estimating material properties. And for liquids, we don't really have a super great way of predicting things, so we're just going to talk about sort of how you mix things together. So for density, and this is sort of the property that we're going to be most concerned with in this particular class, because density allows us to communicate to you guys the flow rate in a volumetric term, which is something that's a bit easier to understand than a mass flow rate, and then convert it into a mass or molar flow rate. So density is going to be one of the most important concerns. So density, right, we know as the mass of something divided by its volume. Now, how we're going to calculate densities for fluid mixtures is we're going to do a very simplified assumption, which is going to be valid for this class, but it's not going to be valid for your Thermo 2 class. In Thermo 2, you're going to be talking about when this is not the case. But we're going to assume volume additivity. And this is generally only true for what they call ideal mixtures. So if I have 1 liter of fluid 1, 1 liter of fluid 2, I mix them together, I get 2 liters. In general, that's not actually true, right? If I have 1 kilogram of fluid 1 and 1 kilogram of fluid 2, I always get 2 kilograms of the mixture. But volume is not a conserved quantity. Based on how the molecules organize in the fluid, if the presence of a second type of molecule disturbs the structure of the first type, then you have to have a volume change, either an expansion or a contraction. Right? Fluids are very, very dense. And so throwing in a molecule of a different shape, right? It's like throwing in like a K'NEX and a Lego bin, right? Lego want to pack a certain way, K'NEX want to pack a certain way, but when you mix the two together, you're disturbing the structures. So sometimes fluids will get denser when you mix them together, if they fit really well together, but most of the time they'll get less dense because they don't fit so well together. But for this purpose here, we're going to assume volume additivity, which allows us to convert this equation here and say volume is equal to the mass over the density. So the total volume, following our assumption of volume additivity, is the summation of the individual volumes of every species that we're contributing to this mixture. We're going to substitute in this expression up here so that the total mass of the system is the average volume, the average density, and I put this bar over the top of it. That's a typical notation used for average, having a little bar on top. This is equal to the summation of volumes, which is equal to this right here, summation of all the individual masses divided by all of their individual densities. So from here, we can calculate the average density of a fluid mixture. Another way we can write this is if we divide both sides by the total mass. We have 1 over the density, the average density, is equal to the summation of the mass fraction of each individual component divided by the density of their individual components. This is not the most accurate way, but it is a way that it'll get you 90% of the way there for the most part. And unfortunately for liquids, this is about all I can do, right? Because the prediction of liquid properties is really hard. And so for liquids, we need to know the densities of the individual components for us to have any sort of an accurate estimate. All right, question.
What was the x, sorry?
X is the mass fraction of component I. So this is the mass fraction. And this is equal to the mass of species I divided by the total mass. And so if we divide both sides of the equations by total mass, the mi divided by m turns into the x of I. Okay, so let's move on to ideal gas law. So by a show of hands, who's heard of the ideal gas law? Good. Who feels comfortable with the ideal gas law? Good. We're not going to spend too much time on it. But for the most part, what I want to talk about with the ideal gas law are the assumptions that go into it and different ways of writing it. So typically, well, so let's write ideal gas. Let's get ourselves started here. Right, the ideal gas is an equation of state. Now, what an equation of state means is that it relates the temperature, pressure, and density of a fluid. In this case here, I've written V hat, which is cubic meters per mole, which is related to 1 over the density of the gas. And in this case here, the density units would be different. This would be molar density as opposed to mass density. There are ways to work out. So, any equation of state that relates between temperature, pressure, and density or specific volume of a fluid is typically called an equation of state. Now, in Thermo 2, you'll use an equation of state to calculate absolutely everything. Vapor pressure, enthalpy, entropy, Gibbs free energy. But for our purposes, we're mostly just concerned about calculating the density or the specific volume of the fluid, right? But an equation of state, what we're using these for is sort of like the most basic application of an equation of state. But in reality, you can do a whole lot more with them. So the ideal gas law, typically you'll see PV equals nRT. But you can also write PV hat equals RT. Or if you were to look in a physics or a physical chemistry textbook, maybe in your quantum class, you'll see P is equal to rho RT. Or you could see it as P equals rho KBT, Boltzmann constant. In this case here, KB is equal to the Boltzmann constant, Boltzmann, which is equal to R divided by Avogadro's number. So this expression here is for per individual molecule. This expression here is for per individual mole. But they all communicate the same information. So the Boltzmann constant and the gas constant are effectively exactly the same thing. The only difference is, are you counting the kinetic energy of a gas molecule or the kinetic energy of a mole of a gas? That's the difference between Boltzmann and the gas constant. Superfluous for our purposes, but just in case you see these different expressions, these are all different forms of the ideal gas law. One common application of the ideal gas law is this concept of STP. STP is equal to standard temperature and pressure. And this is at 0 degrees C and 1 bar of pressure. What is the volume of gas? Actually, well, 1 bar or atmosphere. I'm not quite sure if actually it's 1 bar or 1 atmosphere. They only differ by like a percentage or so. Yeah.
I think it's 1 atmosphere.
Is it 1 atmosphere? It depends on which field. So we're going to go with 0 degrees C and 1 atmosphere. That's what I have written down here. Oftentimes atmospheres are kind of annoying to work with because it's 101 kilopascals as opposed to a bar, which is 100. So sometimes a lot of thermodynamic texts relies on bars as opposed to atmospheres, just because that 1%. But ultimately, that's not a big deal. What is the volume of 1 mole of an ideal gas at STP?
22.4 liters.
Bingo! 1 mole at STP is equal to 22.4 liters, which is equal to 0.224 cubic meters. 1 kilomole at STP is equal to 1 cubic meter, because you're timesing them both by 1,000. A lot of the times when you may have seen the ideal gas law used in a chemistry class, you'll see like P1 over V1 is equal to something over something, right? So what we're going to say here is we're going to solve for n. N is equal to PV over RT, right? So if I'm taking a gas, right, imagine I've got it in like a balloon or something like that, okay? Where my number of moles is constant because my balloon is impermeable, the walls are. And I want to transform it from what we call state 1 to state 2. State 1 to state 2. Now you might have heard these terms in your thermodynamics class. What this basically means is state 1 is a collection of variables. Temperature 1, pressure 1, volume 1. State 2 is a collection of variables. Temperature 2, pressure 2, volume 2. So in thermodynamics, when we talk about states, we're talking about the necessary collection of variables that fully define the conditions of the system. So in the case of an ideal gas, that involves only temperature, pressure, and volume, right? And in the case actually of all thermodynamics, that's all you need. So if we want to relate the temperature, pressure, and volume of some initial conditions, we can call that state 1, and the temperature, pressure, and volume of the other conditions, we can just do a mole balance, right? N1 is going to be equal to N2. So we can use our rearranged ideal gas law through this expression here. And we can simply rewrite this as P1 V1 over R T1 is equal to P2 V2 over R T2. And then from here, we can start to simplify things, right? Depending on how we're changing the state. If we are, right, so R in all cases is going to cancel out. P1 V1 over T1 is equal to P2 V2 over T2. If we are performing this state change isothermally, right, we're keeping a constant temperature. These two cancel out. P1 V1 is equal to P2 V2. If we're doing it at constant pressure, V1 over T1 is equal to V2 over T2. Right? And so just using a material balance coupled with the equation of state, we can come up with all sorts of, I think it's called like Charles' law and all these other different laws that you guys talked about in chemistry class. But ultimately, we don't care about the names of those laws. Just do material balance, right? Assume that you've encapsulated your gas in an impermeable membrane, and then you can just transform its properties from there on out. All right. Any questions on the ideal gas law? That's about all we're going to talk about with it. But it's the one you're probably going to use the most frequently in the class. But something that you all have experience on. A definition we want to go over really quickly is called the partial pressure. Now, the partial pressure is a concept that is really only valid when you have an ideal gas. Because in an ideal gas, the pressure of the mixture is equal to the summation of what we call the partial pressures. And we can define the partial pressures, it should be a lowercase p. It's easier to see here than it is here, but it's a lowercase p. Is going to be equal to N of I, so not the total number of moles, but just the moles of species I, RT over V.
Sorry, you said total pressure is
So the total pressure is the summation of all of the individual contributions to the pressure from all of the individual different types of molecules in a mixture. This is a term that's going to be very useful when we start to talk about multi-phase, multi-component thermodynamics, because the partial pressure is going to determine how much of a particular gas condenses into the liquid and how much of a particular gas boils into the vapor phase. But for now, this is sort of a definition I want to tick off the list of something that we've talked about. So if we apply this approximation here, we can say that the mole fraction of species I, which is equal to the number of moles of species I divided by the total number of moles, or we could also write this as Ni divided by the summation of Ni, right? Number of moles of species I divided by all of the species added together. We could say that this is the partial pressure divided by the total pressure. And we can also say that the volume of species I divided by the volume. Right, so this would be the volume of the gas if it were alone. And that's the definition of partial pressure. But it's really mostly only applicable when we're dealing with an ideal gas. When we're dealing with non-ideal gases, you have attraction and repulsion, which means that if the gases are attracted together, we would expect the pressure to be lower because they're less likely to hit the wall. Right? The gases on the interior are sort of pulling them in and holding them close. If you have net repulsion between molecules, then the pressure is going to be higher than you would expect from the ideal gas law. So now we can transition into real gases. Now there are three general strategies. Actually, before we talk about the strategies, let's talk about the assumptions of the ideal gas law. So, let's have a general discussion. Does anyone know what is the main assumption of an ideal gas? Yeah.
All collisions are elastic.
That's one.
No reactions.
No, we can have reactions, but no interactions. Yeah, no interactions. Yeah.
The gases are incompressible.
Gases are incompressible. No, so almost all gases will be compressible. So fluids, though, in general, we will assume that liquids are incompressible. And what that means is that the density is a very weak function of the pressure. But in the case of an ideal gas, we can see that the density and pressure are directly related. But for a fluid like water, we assume it's incompressible. I think we've hit the most important ones. Now, the most important one that we care about is no interactions. So, what criteria can we use in the ideal gas law, right, that would tell us what are the conditions, temperature, pressure, and volume, that would give us a good approximation of the real situation? Low temperatures, high pressures, low volumes, high volumes. Under what circumstances do we expect the ideal gas law to be the most accurate?
Low temperature.
So I have a vote for low temperature. What else we got?
I say like
Low pressure.
Low pressure,
high volume.
high volume.
They're opposites.
So let's take a look at this. Let's talk about the ideal gas assumptions.
Pressure.
So the most important one that we're going to talk about is non-interacting. So let's say we try and visualize a gas. Okay, here's our container, and we have gas molecules zipping around. This one's zipping this way, this one's going that way, and this one's going this way. What property would tell us, what is the average distance between two molecules? I would say the density is a good unit, right? Because if you have a really high density, that means you probably have a lot of molecules that are close together. If you have a really low density, you have molecules that are very far apart. So regardless of if they actually interact, they're so far apart they don't have an opportunity to do so. So if we take one of our expressions here, let's use this form of the ideal gas law, right? The density is equal to P over RT. So as rho goes down, the density goes down, we have fewer interactions. So how can we accomplish a low density fluid looking at the ideal gas law and the relationship between pressure, density, temperature?
High temperature.
So this is accomplished when temperature is high or when pressure is low. So every single equation of states should reduce to this sort of behavior. Everything should become an ideal gas when you have either a high temperature or a low pressure. So let's take a really quick moment here and look at our van der Waals equation of state here, right? So at the van der Waals equation of state, we have P is equal to RT V hat minus B minus A over V hat squared. Right, so the specific volume is equal to 1 over the density. So the specific volume goes to ideal gas behavior when it goes down, right? Sorry, up. Up. Right, so that means a high volume per 1 mole is the same thing as a low density, right? So if we take a look at this and we remember sort of our limits that we did in calculus, as the specific volume goes up, what happens to this term? It goes to 0. As our specific volume goes up, what happens to this minus b term? It just becomes insignificant, right? Like it's 1,000,000 minus 1. Yes, it's not technically 1,000,000, but it's pretty close to 1,000,000. So we can see that as your density goes down, your specific volume goes up, all of these really fancy complex equations simplify just down to RT over B. Right? And then we get our ideal gas law behavior back and reestablished. So the reason why I spend some time talking about this, so non-interacting, and another important assumption here is low density. They go a little bit hand in hand, but I want to separate them out uniquely right now because of what we're going to be talking about for the non-ideal gases. So how we can correct for different gas behaviors. And this is not the formal development of how it was, accomplished in the scientific literature over the past 200 years, but I think it's a convenient way to look at it, is we can introduce correction factors to the ideal gas law. And we can do it in a couple different ways. So what I'm going to call here is I'm going to say fixing the ideal gas law. Ideal gas law, IGL. So what we can do, let's see. The first attempt, we can improve the assumptions. In this case, low density and non-interacting. Right, so can we develop an equation that doesn't rely on these assumptions? Right, can we somehow account for the interactions? And can we somehow consider the volume of the actual molecules? That's what this assumption here implies, that you don't have to consider the volume occupied by the individual molecules. And so for this approach, we get to what they call a cubic equation of state. EOS, equation of state. Another option is we can introduce plus minus corrections. And in this case here, this accounts for interactions. And this gets us to the virial equation of state. And on your sheet, you should see virial equation of, yep, I have it here. The top one is the virial equation of state. If you look at it, it looks like the ideal gas law, but you've got an additional term that you've added on to the end. The van der Waals, SRK, and the Peng-Robinson, you can see there are much more complex equations going on. And the last one is we can introduce times minus, or times divide scaling factors. And this approach here is empirical, meaning we don't actually know the underlying physics necessarily of what's going on. We just say, you know what, let's just measure the properties of a lot of gases, add them together, and say, yeah, it's not 100% accurate, but it's better than just the ideal gas law. And this is where we get the compressibility factor. So Z is equal to the compressibility factor. Okay, and you should see on your handout, we have different charts for the compressibility factor. 1, 2, 3. And they cover different pressure and temperature ranges. right? So we'll talk about those. I don't think we'll have time to talk about that one today, but we'll get to that on Monday then, because we'll have the practice exam on Friday. Okay, so the first one I'd like to talk about is the cubic equation of state, because that one has the most sort of interesting underlying physics associated with it. So we're going to break down the cubic equation of state. Now, why do we call it a cubic equation of state? That's because we can write the equation like this. B cubed plus some coefficient, b squared plus beta b plus some equals 0. Okay, so we can rewrite the equation of state like this. Now, the ideal gas law only has basically v to the power 1. So the cubic equation of state has the volume to the third power, so you've got a lot of additional terms going on in here. So what we're trying to accomplish with the cubic equation of state is we want to take into account these two approximations here that were made for the ideal gas law and find a way to mathematically represent them. And so to illustrate this, we're going to look at the van der Waals equation of state. P is equal to RT. So B is equal to the excluded volume. And what this means, this is the volume that is physically occupied by the gas. According to the ideal gas law, you can compress your fluid infinitely small, right? Because your gas molecules don't exist, right? You don't consider the volume of the molecules themselves. In this case here, this B term is physically the volume of the molecule itself, right? So you'll reach a point where you cannot compress it anymore because this will go to infinity, right? As you get closer and closer and closer to shrinking your box down to the size of the actual molecules themselves, your pressure shoots up to infinity and you can't do anything beyond that point. In the ideal gas law, you can go all the way down to 0. And A accounts for the interactions. Now, if you look at this here, we have that B, on your sheet it has the same thing, is RTC over 8PC. Interactions, you have 27R squared TC over 64PC. Oops, not TC, TC here. PC is equal to the critical pressure, and TC is equal to the critical temperature. And in a moment, we'll stop and we'll look at some videos actually of what I'm talking about here. Okay, so really quickly though, if we look at this equation and we rearrange it, you can kind of start to see that this is actually cubic, right? Because if I want to combine these two terms and add them together, right, you have to do that cross multiply where I do times this side by v squared and times this side by v minus b. So you can see that times in v squared times by v, that'll give us volume to the cubic power. So this is truly a cubic equation of state. Who has heard of the critical temperature and the critical pressure before? Handful of folks. Question.
Does that say 27 over 64?
Yes, 27 over 64. We'll talk about where we get this from in a bit. So, the critical pressure and critical temperature, this is a material property that we have no control over. Every fluid has a critical point. This is the point where gases and liquid become indistinguishable, right? And I will show a video of what this means because I'll be honest, it was an embarrassingly long time. So the critical point is best to visualize by looking at a phase diagram. So a phase diagram, typically we draw these, what they call a PT diagram. Temperature's increasing this way, pressure's increasing this way. So if I have a low temperature, high pressure material, what phase of matter am I typically going to be in? Low temperature, high pressure. Solid. All right, if I'm at a low pressure and a high temperature, what am I in?
Gas.
Gas. Right? And so how it looks is we connect the dots, it'll look something like this. And we have a liquid in between, sort of the moderate phase, right? This point right here is called what? Triple point. This point right here is called what? Critical point. This is the critical point. So one notion with the critical point is that you can transition from a gas to a liquid or a liquid to a gas without actually undergoing a phase transition. So if I go from a liquid to a gas, what happens to my liquid?
Evaporates.
It boils. So evaporation is slightly different. Evaporation is actually a multi-component property. Right? So evaporation requires at least two materials in the system. So in the case of water and air, you need that air to support water to evaporate. But if this is a single phase system, only water in a jar, and I want to boil it, I have to heat it to a certain temperature, or I have to lower the pressure, right? Heating it, I phase transition this way. Lowering the pressure, I phase transition this way, right? And that's what boiling water is, right? It's a visual phase transition where you have liquid and gas coexisting together. Those are the bubbles inside your pot of boiling water. Now the critical point is you can go around like this, go through the critical point, and you'll never actually see two phases coexisting together. Right? What happens is that your liquid becomes less dense and your gas becomes more dense until their densities meet. Now this curve right here, this curve gives you the vapor pressure. That's the pressure that the liquid is sort of exerting on its surroundings, wanting to boil. So fluids boil when they reach their vapor pressure. So the vapor pressure of water at 100 degrees C is 1 atmosphere. That's when the vapor pressure of the water meets the vapor pressure of the surroundings. The critical point, right, that's the vapor pressure at the critical temperature. That's PC and TC. Now the reason for this is if we look at TR, that's reduced temperature. Which is equal to T, the actual system temperature, divided by the critical temperature, and PR is the reduced pressure, which is equal to P over PR. So how these equations are developed, and how we get this weird 27 over 64 and 1 over 8 type terms, is we assume that all fluids behave exactly the same, but not as a function of the temperature and pressure, but as a function of the reduced temperature and the reduced pressure. So what we're saying is that every single material has this phase diagram here, and they all basically do, more or less. But the difference between nitrogen and some heavy gas like water vapor or vapor ethanol is that nitrogen is at a different point on its phase diagram, higher or lower than the critical point compared to the other fluid. Yes?
Is that supposed to say PC under pressure?
Yes, it
Okay,
is.
sorry, making sure.
Thank you. P over PC. Okay, so we don't have time to go through the rest of the equations, but we'll talk about them on Monday as a rehash. But what I wanted to do is actually show some videos, since we're talking about the critical point of what's going on and what I'm talking about here. So let's see if I can get this set up in enough time. Center projector on, so that we can actually see what's going on. And I'll include a link to these videos in the description as well on the YouTube page. So the first one we're going to watch, assuming that this all connects, you can actually see I'm having some issues with it. The first video we're going to watch is an example of the triple point. And this is for a compound called tert-butyl alcohol, T-butyl alcohol. Please work and connect. There it is. Okay. So this is the alcohol right here. So what they're doing is they've attached this to a vacuum pump, and I have it written down here. The triple point for tert butyl alcohol is at 21 degrees C, so right about room temperature, but 5 kilopascals. So it's about 5% of an atmosphere. So what's happening is that they're lowering the pressure and it's starting to boil, and it's going to be dropping the temperature. So if I know what's going on, they probably have this on a hot plate to heat it up, because as you boil stuff, it cools down. So now it's stopped boiling. 2 minutes later, blah, blah, blah. Eventually, you'll start to see it freeze. There it's going. So you're getting some solid crystals forming here. And you've got a lot of liquid, and it'll start boiling again, and then you've reached the triple point. So you have all three phases in coexistence. So you have liquid, solid, and the vapor phase, all coexisting together. And so this is a really nice material that you can do the triple point in a lab demonstration. So if I was more fun of a professor, I would have it set up here and we could all visualize it. But we're just going to do a video. Okay, so that's the triple point, which I think is kind of cool just to see how it all goes on. But it's you kind of have to balance it. You got to stay right at that conditions. Now, the next one is going to be the most exciting video of water boiling you have ever seen in your life. So I'm just going to skip ahead. So with water boiling, and I wanted to point this out so we can see the differences between this and the critical point. Right? We're visually seeing the coexistence of the water bubbles and the liquid water. You can see air bubbles are nucleating on the surface, and you have clearly a phase transition, right? Bubbles are forming, they're boiling out, and you have the water vapor disappearing. Super exciting, right? I know everyone's seen water boiling. But I want to use this information. See, lots of bubbles, lots of stuff going on, right? You have the coexistence of the two phases. Now, we're going to look at the critical point of CO2. Now, CO2 is, again, another really convenient one to look at the critical point, because its critical temperature is 31, and its critical pressure is 73 atmospheres. So you don't have to heat it up. All you have to do is pressurize CO2, and you can make it sort of an in-class demo. Again, if I was cooler, we would do that, but too bad. So what's going on now is that they're just so they've pressurized it, and they're either heating it or cooling it. And so we can see that this is the liquid phase and this is the vapor phase. But as you approach the critical point, you can start to see, you don't see bubbles forming, right? They just sort of kind of merge together, right? So what's happening is that the density of the gas phase is increasing while the density of the liquid phase is decreasing. So as you reach the critical point, right, you don't really see an abrupt phase transition. You just sort of see a disappearance of the interface. Right? So when I have water vapor inside of water, you can see the bubble, you can see the interface. Right? The reason why a bubble forms is because of a property called surface tension. Right? Those two phases, they don't want to mix. They actually don't like each other. Right? The liquids and gases don't much care for one another. Now, the critical point, oftentimes when I was a student, they would refer to it as saying the meniscus disappears. And I go, wow, that's so fantastic. I have no idea why I should know what that means or care about. Right? But the more important thing to understand is the reason why the meniscus disappears, right, which is caused by surface tension, right? The meniscus is that shape that forms when the two fluids don't want to be in contact, so they kind of minimize their contact area. That's the same reason why bubbles are spheres, right? Because spheres are the most volume you can contain with the limited amount of surface area, right? That's why rain droplets are spheres. That's why air bubbles are spheres, right? It's because that maximizes the volume with minimizing the contact area. So in the boiling case, you saw droplets forming, right? You had surface tension. You had those two phases that had different properties. You have a discontinuity in the density going from the gas phase to the liquid phase. And that causes the fluids not to like to be around each other, and then they can encapsulate themselves in these droplets or bubbles. Now, in the case of the critical point for the CO2, however, that doesn't happen. right? We have an interface here when we have the coexistence of two phases. But as you reach the critical point, the properties of the liquid are exactly the same as the properties of the gas. So you cannot tell a difference between which is gas and which is liquid. Which in that case happens, right? If the property is the same, well then maybe the liquid's on top and the gas is on bottom, right? But in reality, they just merge to a single fluid without ever undergoing a phase transition. No boiling, no crystallizing, nothing like that. It just disappears. Right? And that's because the density of the liquid now matches the density of the vapor, and that's what we define as the critical point. Yes?
What does this have to do with like latent heat or anything like that, of like vaporization?
Doesn't, so what it does have to do, so if you go back to our phase diagram here, as you get closer to your critical point, the properties of your liquid and the properties of your gas get closer and closer and closer together, right? So that means down here, close to your critical point, there's a huge difference between your liquid and gas properties. So the latent heat of vaporization is really big, right? Because you've got a big difference. But as you get closer and closer and closer to your critical point, the properties of the gas and liquid get closer together, and the energy it takes to phase transition gets smaller and smaller, right? And so the difference between the heat capacity of a liquid and the heat capacity of the gas tells you the heat of vaporization as a function of temperature. Okay, so I'm a bit over time. Hopefully the video was a useful demonstration, but I'll post the links in the description. All right, see you on Friday.